Hello, my good friends. My name is Tete Jacob Sirichi, and welcome to my online teachings. We'll be discussing discrete mathematics today, and our attention will be on relation. Before the video ends, we'll look at a very important property of relation, which is equivalent relation and equivalent class. Before the video ends, we'll look at what an equivalent class is, how to determine if a relation is an equivalent relation, and when a relation is an equivalent class. This will be a very interesting engagement, I promise you. So come along. So we start things off with an equivalent relation. So a relation R defined on a set A is said to be equivalent relation if it satisfies three conditions. Thus, it is reflexive, it is symmetric, and it is transitive. Please, did you watch my videos on how to determine if a relation is reflexive, if a relation is symmetric, and if a relation is transitive? Please do that on YouTube, or you can get that video at the end of this video. So now, when we say that a relation is equivalent, we'll take a sample relation defined on a particular set and find out whether it satisfies an equivalent relation. So our first example says that the relation R is defined on a set A equal to the members 1, 2, 3, 4 as R equal to a set with the ordered pair 1, 1, 1, 2, 2, 1, 2, 2, 3, 3, and 4, 4. We should determine whether or not the relation R is an equivalent relation. So remember, we said a relation is an equivalent relation if it satisfies three conditions. If it is reflexive, symmetric, and transitive. I hope you get that. So when do we say relative is transitive? That's if A belongs to the relation for all A, B is a member of the set A. So what do we mean? It simply means that when we have all the self-loop relations in the relation, then that relation qualifies to be a reflexive relation. So you can see that 1 relate 1. Look at this. We have 1, 1. 2 relate 2. We have 2, 2. Do we have 3, 3? Yes. 3 relate 3. Then we have 4, 4. So we can say 4 relate 4. Therefore, the relation is reflexive. I hope you get that. Now we check the symmetry property. Remember the symmetry property? We say if A, B is a member of R, then B, A must also be a member of R for all A, B is a member of the set A. I hope you get that. So let's check. 1 relate 2. So you can see 1 relate 2. We check whether 2 also relate 1. Do 2 relate 1? Yes. So 2 relate 1. Do you have any other idea? No, we don't have any. The rest are self-loop relation. All we need then is it will still be the same. Hence, the relation is what? Is symmetric. I hope you get that. So we check for all, we check for the transitive property as well. So I want to check for the transitive property. Remember the transitive property, we say if A relate B and B relate C, then A will also relate C. For all A, B, C being a member of the set A. I hope you remember that very well. So I use table to get an easy identification. So my first listing I'll write the ordered pair 1 comma A comma B. That's listing all these ordered pairs. So I have 1 1, 1 2, 2 1, 2 2, 3 3. Then the last one is what? 4 4. Now I'll have B comma C. B comma C. So my B comma C, that means I will list the relations where this place 1 start. So where are the relations that 1 start? We'll have 1 2. When I come here, the relation that 2 start, we have 2 1 as well as 2 2. So with the relation that 1 start, there is also 1 1. So we have 1 1, then 1 2. The relation that 2 start, 2 1, 2 2. Please do well to check out my videos on how to determine if a relation is transitive. It will help. Now the relation that 1 start, we have 1 1, then 1 2. Now the relation that 2 start, we have 2 1, then 2 2. This one, the relation that 3 start, we have 3 3. The relation that 4 start, we have 4 4. Then we have the other column, which is A will relate C. So A will relate C. We pick the first entry here and pick the second entry here. So we have 1 1 here, then 1. We have 1 here, then 2, 1 and 2. So here we have 1 1 again. Then we have 1 2, 1 comma 2. Then this place we have 2 1. So 2 comma 1. Then we have 2 2, 2 comma 2. Then this we have 2 1, 2 comma 1. Then 2 2, 2 comma 2. Then this will have 3 3. Then this will have 4 4. The next thing is that you check whether all these relations here are a member of R. All the other pairs are a member of R. 1 1 is here, 1 1. We have 1 1 here, 1 1 is in the relation. 1 2, 1 2 is in the relation. 1 1 is there, 1 2 is there. 2 1 here, 2 1 is in the relation. 2 2 is here, 2 2 is in the relation. 2 1 is there, 2 2 is there. 3 3 is in the relation. 4 4 is in the relation. When it happens like that, we say the relation is transitive. Then we can say the relation is transitive. I hope you get that. So since the relation is transitive, it is symmetric and reflexive. We can conclude that our relation can conclude that the relation R defined on the set is equivalent relation. I hope you get that. This is not anything difficult. Please do well to check out my videos on how to determine if a relation is transitive on YouTube. It will help you understand this better. Now we'll solve another example on this. So solve our second example. They say a relation R equal to the set with the ordered pair 1 1 1 2 and 2 1 is defined on a set A with the members 1 2 3 4. We should show whether or not R is an equivalent relation. Remember, we said a relation is an equivalent relation if it is what? If it is reflexive, symmetric, and transitive. I hope you know this by now. So when we say a relation is reflexive, a relation is reflexive if we have AA belonging to the relation for all A, B is a member of the set A. So what we do, we check all the self-loop relation of the set. if it exists. So we need 1, 1. Is there 1, 1? Yes. Then we can say 1 relate 1. We need 2, 2. Do you have 2, 2? No. So we say 2 does not relate 2. We need 3, 3. Do you have 3, 3? No. We can say 3 did not relate 3. We need 4, 4. Do you have 4, 4? No. So we can say 4 did not relate 4. Then the relation is not. So the relation is not reflexive. I hope you get that. With this, it's even an enough reason to disqualify the relation for being equivalent relation. But let's proceed and check the rest. So for transitive, symmetric, we said a relation is said to be symmetric if A relate B is a member of R. Then B relate A must also be a member of R for all A, B being a member of A. So what do? We find all this, any alternating relation. If it exists, then we don't have problem. So let's look at it. 1 relate 2. 1 relate 2. But so we check whether 2 also relate 1. Yes, 2 also relate 1. Then we don't have problem. You see that 1 relate 2 and 2 relate 1. Then we can say the relation R is symmetric. Now we check the transitive property. So we say a relation is said to be transitive if we have A relating B, then B relating C, then we can say that our A will relate C for all A, B, C be a member of the set E. Please check out that video. We did all these things there. It will help you. So I will use a table to make it easy for me. I'll have the other pair where A relate B. So I'll just list the relation 1, 1, 1, 2, and 2, 1. Now I need B relating C. So now I'll select the ordered pairs where here 1 starts. So we have 1, 1, then 1, 2. Then here the relation where 2 starts. We have 2, 1. Then here the relation where 1 starts. So we still have 1, 1, then 1, 2. That's for A relating B. Now we'll find our decision maker. That's A must relate C. So we'll pick the first entry here and the second entry here. So 1 here, 1. So we'll have 1, 1. 1 here and 2. We have 1, 2. I hope you get that. We have 1 here, 1. So we have 1, 1. Then 2 and 1. So we have 2, 1. Then 2 and 2. We have 2, 2. Now you check whether all these ordered pairs are a member of a relation. So let's check. 1, 1, 1, 1 is there. 1, 2, 1, 2 is there. 1, 1 is there. 2, 1, 2, 1 is there. 2, 2. But there is no 2, 2 there. So we can say that the relation is not transitive. So since the relation is always symmetric, it's not transitive, it's not reflexive, the relation ceases to be an equivalent class. So we said the relation is not an equivalent relation. It's not an equivalent relation since it is only symmetric and not reflexive and transitive. I hope you get this. This is very, very interesting. When you check whether it is reflexive, symmetric, and transitive, if one of them, if it doesn't obey only one property, then it ceases to be an equivalent relation. We'll solve one last example on this, which involves proving. So our third question says that we should show whether or not the relation R equal to the ordered pair AB, where A minus B is an integer, is an equivalent relation. We should show whether it is an equivalent relation. Remember when we said a relation is an equivalent relation if it is what? If it is reflexive, symmetric, and what? And transitive. I hope you get that. So we check for all. So for reflexive, I want to check for reflexive. A must be a member of R for all A, B be a member of the set, maybe A. Maybe a set, that set is defined on the relation R. So what we have, we check A minus A and see if it is an integer. A minus A is 0, and 0 is an integer. So we don't have problem. Then we can say the relation is reflexive. I hope you are getting all this. We check for the symmetric property. Remember, for symmetric, actually, yes. We said that if we have A, B, be a member of the relation, then we must have B, A, be a member of the relation for all A, B, be a member of the set A, defined on that relation. So we check whether A minus B is an integer, B minus A is an integer. If it is an integer, then the relation is symmetric. Remember, if you have A minus B, it will always be an integer. Remember that. So if A is 5, B is 2, 5 minus 2 is 3, and 3 is an integer. For all numbers in the world, it will be an integer. Then we check B minus A. B minus A will also be an integer for all. Sure. So we can say the relation is what? Is symmetric. I hope you get it. Now we check the transitive property. So for transitive property, we say if A relates B, then and B relates C, then A must also relate C. I hope you get that. Amen. For all A, B, C be a member of A, or be an integer in this case. So what we have? We check. So remember, A minus B is an integer. True. Then B minus C is also an integer for all values in the world. So if A minus B is an integer and B minus C is an integer, then we can say A minus C is also an integer. I hope we get that. Then the relation is what? Is transitive. This is very, very easy. So since the relation is transitive, it is symmetric and reflexive, then the relation is an equivalent class. So we can say, therefore, the relation R equal to A, B, be a member of the relation where A minus B is an integer, is an equivalent class. Equivalent relation. I hope you get that. This is very, very simple, and I know you understand. The next stop is equivalent class. So we say a relation R defined on a set S is said to be an equivalent class to the set S if it satisfies three conditions as well. That's if the relation R is not an empty set. That's it has members. Then if any of the other pairs, A intersection B, or any of the two sets in the relation, the intersection of them is not equal to R. Please, let's correct that. When the intersection of two sets is not a member of R, then when any of the other pairs in the relation R, the union of them is equal to, or the union of all the members in the relation R is equal to the set S, or is the same as the set S. If a relation satisfies these three conditions, then we say the relation is an equivalent class to the set in which it is defined on. So now we take some sample question and see how to determine if a relation is an equivalent class to a particular set. So our example says that we should determine which of the following relations defined on a set S equal to the members 3, 4, 5, 6, 7 is an equivalent class to the set S. And R1 is with a member of a set of sets 3, 5, 3, 6, 7, 4, 5, 6, also as another set in that order. So how do we do this? So solution, you determine whether it satisfies all the three conditions of being an equivalent class. If it satisfies, then we say it's an equivalent class. If it doesn't, then it is not. So we say a relation is defined on a set is said to be an equivalent class if it is not an empty set. Please. So you check all the relations here. None of them is an empty set. They all satisfy the first condition. Then the second condition, if A intersection B is not equal to the relation. That when you check A intersection B, it's not a member of the relation R. Then the last one, if A comma B union B comma A is an equal set to the set S. So we check for all. So this one we check the first. So R1 is not an empty set. First condition satisfied. We check the second condition. We find the intersection of the two sets. So 3, 5 intersection 3, 6, 7 will be 3. I hope you get that. The intersection means the members that are in these two sets is 3. So we check whether 3 is a member of R1. 3 is not a member of R1. Good, we are good to go. So we check 3, 5 against 3, 4, 5, 6. 3, 5 against 4, 5, 6 is an empty set. The intersection is an empty set. And there is no empty set in the relation R1. It's also satisfied. We check the 3, 6, 7 against 4, 5, 6. 3, 6, 7 against 4, 5, 6. The intersection here is 6. Do we have the set 6 in the relation R1? No. Then it satisfies that condition too as well. We check the third condition. We find the union of all the sets and see the outcome. So 3, 5 union 3, 6, 7 union 4, 5, 7. It means we put all the sets together. What are we having? We have 3, we have 4, we have 5, we have 6, we have 7. Check whether it is the same as the set S. It's the same. Since it's the same, it satisfies that condition too. Then we can say our R1 is equivalent class. I hope you get that. It's an equivalent class. Very, very simple. Now we check the R2. So check first whether it is an empty set. Is it an empty set? No. So first condition satisfied. We check the second condition. 3, 4, 6, intersection 7. So the intersection is an empty set since there is no common element. Since it's an empty set, we find whether empty set is a member of the relation R2. It's not, then it satisfies that condition too as well. Now we check the third condition. We put the union, that's we put the two sets together. When we put them together, we have 3, 4, 6, 7. Is 3, 4, 6, 7 the same as 3, 4, 5, 6, 7? No. 5 is missing there. Then it is not. So it doesn't satisfy that condition. Since only one condition is missing, we say R2 is not equivalent class. I hope you get that. So we check for our R3. So R2 is not equivalent class. R1 is equivalent class. Let's check for R3. Please pause the video and try to see if you determine whether it is an equivalent class or not. After that, you compare your answers with mine. So the first, we'll find out whether it is an empty set. R3 is not an empty set. There are at least 8 elements in it. Now we'll find whether A intersection B is a member of the relation. So 3 intersection 4, 6 is an empty set. We don't have empty set in the relation. Good. 3, 5, the intersection is an empty set. We don't have empty set in the relation. We are good to go. 3, 7 is an empty set. We don't have empty set in the relation. We are good to go. Now we check for 4, 6, and 5. 4, 6 intersection 5 is an empty set. Since there is no common element, it's satisfied. Now we have 4, 6 intersection 7. It's also an empty set. We don't have empty set in the relation R3. It's satisfied. 5 intersection 7 is an empty set. We don't have empty set in the relation R3. Then it satisfies all those conditions. Now let's check the third condition. We find the union of all the sets in that. So the union, we put them together. We have 3 here. We have 4. We have 5. We have 6. We have 7. We check whether this is the same as the set S. So 3, 4, 5, 6, 7. 3, 4, 5, 6, 7 is a member of the set S. Then it satisfies the third condition too as well. Then we can say our R3 is equivalent class. I hope you get that. I hope you had the same answer. Now let's check for the last one, which is R4. So we check whether it is an empty set. Is it an empty set? No. So it satisfies that condition. Now we check the intersection. 5, 6, intersection 5, 7 is 5. Is the unit set 5 a member of R4? No. Then that condition is satisfied. We are good to go. So we check for the union. When we put them together, we get 5, 6, 7. Is 5, 6, 7 the same as the set 3, 4, 5, 6, 7? No. 3, 4 is missing. Then it is not equal. Since it's not equal, that condition is not satisfied. Then we can say R4 is not equivalent class. I hope you get the understanding of this now. So our R1 is equivalent class, R2 is not equivalent class, R3 is equivalent class, R4 is not an equivalent class. I hope you get this. Now we'll look at another direction to equivalent class. So please remember to subscribe to my YouTube channel before you sign out. Let's look at our last question on this. They say the set S equal to the members 1, 2, 3, 4, 5, 6, 7, 8, 9. And we have x, y is a relation if x minus y is divisible by 3. For all x, y is an integer. We should find the equivalent class of the set S. Then after that, we partition those classes. So how do we do that? So it simply means that we take two ordered pairs here. If you find their differences and 3 can divide, then it will form that class. It will be a member of the set of that class. So if it doesn't, it's not. So we check. Let's subtract the smaller one from the bigger one so that you understand. 2 minus 1 is 1. 3 cannot divide 1. So it can't form that class. 3 minus 1 is 2. 3 cannot divide 2. So it doesn't form that class. 4 minus 1 is 3. 3 can divide 3. Then we can say 1 and 4 can be in a class. I hope you get that. Then we go 5 minus 1 is 4. 3 cannot divide 4. 6 minus 1 is 5. 3 cannot divide 5. 7 minus 1 is 6. 3 can divide 6. So we can say 7 can be in that class. However, check whether 7 minus 4 can also be in that class. 7 minus 4 is 3. And 3 can divide 3. So these are members of this. Let's check. 8 minus 1 is 7. 3 cannot divide 7. 9 minus 1 is 8. 3 cannot divide 8. Then we can say this is one class. Now let's see another class. Now we can take 2. So 2 minus 1 is 1. 3 cannot divide 1. 3 minus 2 is 1. It can. 4 minus 2 is 2. 3 cannot divide 2. 5 minus 2 is 3. 3 can divide 3. Then we can say 2 and 5 can be in the class. Then 2 minus 6 is 4. 3 cannot divide 4. 7 minus 2 is 5. 3 cannot divide 5. 8 minus 2 is 6. 8 minus 2 is 6. 3 can divide 6. So we can say 8 can be in that class. However, check. 8 minus 5 is 3. And 3 can divide 3. Then we can say this is the members of the class. You can check the last one. 9 minus 2 is 7. And 3 cannot divide 7. Let's look at another class again. So now we take the 3 and partition it against them. 3 minus 1, 2. 3 minus 2, 1. 4 minus 3, 1. We count. 5 minus 4 is 1. 5 minus 3 is 2. 3 cannot divide 2. 6 minus 3 is 3. 3 can divide 3. Then we can say 3 and 6 can be in a class. Now let's check. 3 minus 7 is 4. 3 cannot divide 4. 3 minus 8 is 5. 3 cannot divide 5. 3 minus 9 is 6. 3 can divide 6. Then we can say 9 can be in that class. However, check again. 9 minus 6 is 3 and 3 can divide 3. Then we can say this is the equivalent class of the set. So the equivalent class are 1, 4, 7 as one set, another one 2, 5, 8 as another set. Then we'll have 3, 6, and 9 as another set. Then the question says we should partition the class. So partition that class means putting them into a big set. So we have 1, 4, 7 as a set in another set. Then what again? We have 2, 5, 8 as a set in another set. Then 3, 6, 9 as a set in another set. So this is the partition of. So we can say this is even a relation. So this particular relation, if you check, is an equivalent class to the set S. We'll end it here today. Please remember to subscribe to my YouTube channel, and I'll indulge you to check my other videos on relations. Until we meet again, my name is Kepsi.